In Module 10, we're going to look how can we handle uncertainties associated with the definition of our joint probability density f of x, when the parameters associated with the marginal distribution for each of the random variable involved in our reliability analysis are themselves uncertain. So if we recap what we've seen over and over since the beginning of the course, x is our vector of n random variable involved either in the resistance or solicitation model. F of x is their joint probability density, and g of x is our limit state function. So the joint probability density is represented by a 2D surface here, represented by contour. We have our limit state surface g of x equals 0, or a limit state function is going to be negative here, positive here. This is our failure domain in pink. And so far, we've always assumed that we knew the parameter involved in the joint probability density for all of our random variable. But what if we don't know them exactly? What if the parameters involved in there that are not represented explicitly are themselves uncertain? What if the same thing, we have parameters involved in the definition of our limit state function? How can we handle the uncertainties associated with those parameters, and how are they going to influence or reliability for our component or structures? So what to do when both theta f or theta g, those associated with the joint probability density or the limit state function, are described by random variable. So not only we have random variable x's, we also have random variable defining the parameter involved our joint prior probability density or limit state function. So take, for example, if we have a normal distribution for f of x. So implicitly, when we say f of x, we assume that we know the parameters involved in the definition of that probability density. So here we can explicitly express the dependency upon those parameters. And we do so by using that semicolon. So we're going to put on the right of that semicolon here the parameters that we consider as being unknown. So in that case, what we're going to say that univariate Gaussian distribution is parameterized by mu, the mean, and sigma, the standard deviation. If we assume that mu is known and it's fixed, it's 0, we're just going to assume that here we want to play with sigma, the standard deviation. So we can plot this univariate Gaussian distribution with respect to different values of sigma. So you can see here the dispersion gets wider and the distribution gets shallower as we increase the value of sigma. Now, what happens if we want to say that sigma, we don't know exactly what values it takes, it can take a probability density. So depending what are the realization of sigma, if it's 2, you see it's that slice that describe f of x. If it's this one, it's this one. If it's 1, it's going to be this one. Okay? So we want to be able to express what is the probability density for the parameters involved in f of x to describe our uncertainty about those parameters. And we want to factor in that uncertainty in the calculation of our failure probability. We want to know how the uncertainties on the parameter of f of x influence our evaluation of the failure probability. So this is the problem we're trying to tackle here. So first, we're going to do so by looking at conditional failure probability. How the probability of failure depends upon the specific value that theta, the parameter either associated with the f of x or g of x, what specific value it takes. Second one, we're going to look at how can we use a point estimate. So p hat for our probability of failure, where we only evaluate the failure probability for one specific set of parameter theta. So that could be, for instance, the mode of the parameter PDF, its median, or any other point estimate. Second one, we're going to look at the predictive estimation. So in the predictive estimation, what we're going to do is that we're going to build the joint probability density between PF and the values of theta, and we're going to marginalize the uncertainty associated with theta to obtain what we're going to say our predictive estimate for theta. And finally, we can build confidence region around PF, meaning that we want to have a lower bound and an upper bound on the possible probability of failure. So this is what we already saw in the introduction. We're going to look at the conditional failure probability. Before that, we're going to build a bit about nomenclature. We're going to look at point estimate for our probability of failure using a single set of values for the parameter theta. We're going to look at the predictive estimate for our failure probability. We're going to look how can we define a confidence region for PF that will contain a given amount of reliability target defined by alpha. So that put us here at our second tool in our toolbox. How can we include the uncertainty we have about the uncertainty associated with either f of x or g of x into our calculation of the failure probability? So in terms of nomenclature, theta f is going to represent all the parameters involved in the definition of f of x. So up to now, we've always defined f of x like this, with an implicit dependency upon the parameters involved in its definition. Here, we're going to explicitly represent the dependency upon those parameters by using that semicolon. And what's going to be on the right of the semicolon is going to be those parameters. Like in the case of the normal, defined by the mean value and the standard deviation, we're going to put them on the right-hand side of the semicolon. Those uncertain parameter could also be involved in the definition of our limit state function. Say if on my limit state function is x1 minus x2 to the power theta j could itself be an unknown described by a random variable. So here, instead of referring specifically to theta f theta j, we're going to consider both generically as simply theta, parameters that are unknown. So f of theta is going to be the prior probability density for our parameter theta. In this case, if I have many theta, is going to be a joint prior probability density. F of x semicolon theta is going to be the conditional joint distribution for x given theta. So in the case of the failure domain for some parameter involved in my limit state function, I'm going to say I can have a conditional failure domain. So theta is my failure domain depending on for x. So it's saying it's a failure or survival domain, and that can depend on theta g. So this is going to be my failure domain as the values of x given theta, such that g of x is less or equal to 0. So let's look at our first estimate. Is going to be a point estimate. Okay, sorry, before looking at that point estimate, let's define what is a conditional probability of failure. And so let's look at how will it apply in the context of a component failure. So we're going to define our conditional failure probability as PF that is explicitly dependent upon a value of theta. So that corresponds to the integral of my joint probability density of f of x that is now explicitly dependent upon theta. And we want to integrate that joint probability density over omega, my failure domain. And here, if I want to go from my conditional failure probability, I can also retrieve my conditional reliability index by simply reversing the traditional relationship where PF equals the standard normal CDF of minus beta. If we reverse that relationship, we're going to get beta equal the inverse of my standard normal CDF of 1 minus PF. So here, let's go back to the same example we saw in chapter 6, where we want to look at the failure of that bar subject to a tensile force S, and that is defined by an inherent resistance R. Sorry. So in this case, I'm going to say that D, the dimension of my bar, so the cross section, is modeled by a log normal random variable. S is a Gumbel random variable, which is going to be the tensile force applied on it. So my resistance is going to be d squared times f of y. So the cross section times my yield strength, which is going to be here 0.3 kilometer per square meter. We assume that d and s are independent, such as my limited function is my resistance minus my solicitation. So here we're going to assume that mu d and sigma d, the mean for the cross section is 10 millimeter. Its standard deviation is 2. Those are given. But what if the mean for my solicitation or my standard deviation is unknown? How do I handle this? So I'm going to make here a conditional probability of failure, conditional upon mu s and theta s, where each of those grid points that you see here would represent one reliability analysis, leading each to one probability of failure. So here I just simply build two for loops and did a form analysis for each possible combination of mu s and sigma s, what would have been the failure probability. And then I trace or I plot those results on such a plot. So we can see that as the mean of the isolation increase, I'm going to increase my probability of failure. Okay, so this is what would be the expected result. So now we're going to say, okay, what if mu s and sigma s are not necessarily unknown? We're going to describe what is our knowledge of what could these parameter value be by random variables. Okay, let's assume that my knowledge of mu s is described by a log normal random variable, sigma s also by a log normal random variable. And we're going to see three ways of including this knowledge into include its effect into our calculation of the failure probability. So the first one, we're going to look at the point estimate, PF at, where we're going to evaluate our failure probability using only one set of parameter theta. So for instance, could be the mean, the mode, the most likely value. We're going to see that this is not really a good choice. The second one is, how can we use a predictive estimate? So in that predictive estimate, we're going to build a joint between our failure probability and our knowledge of theta by multiplying both together. So the conditional failure probability conditional on theta times my probability of theta, multiply the two, I'm going to add the joint, and I'm going to marginalize all possible values of theta. So that's going to be my predictive estimate. This is a much better choice than my point estimate. We're going to see why. And finally, my third option is to build a confidence region. Okay, so to have a lower and upper bound to include what or where my failure probability could be in order to attain a given level of confidence 1 minus alpha. So the first one we're going to see is the point estimate for PF. We're going to denote it as PF at. So PF at is basically my failure probability evaluated at a point estimate theta at. And this point estimate could be either the mean value for theta, could be its median, could be its mode, this most likely value, or any other point estimate. But there's a problem with this way of proceeding is that it neglects the uncertainty associated with my parameters theta. So what can we do in this case if we apply it to the example of our bar subject to a tensile force? We're going to again assume that mu d is 10, sigma d is 2. We're going to have the mean for the solicitation described by a log normal random variable, the standard deviation by the log normal random variable. And these four parameters are described here. So the mean of mu s is 15. The standard deviation of mu s is 5. The mean of sigma s is 5. The standard deviation of sigma s is 2. Okay, and we want to include this uncertainty and see how is it going to affect my probability of failure. So if I use a point estimate, I'm just going to use one point to evaluate my probability of failure. So it's like in the map of what we have for a conditional probability of failure, I would evaluate the height of this map either at the mode or the mean. So if we use here in cyan the mean, we're going to have a failure probability of 0.083. If I evaluate at the mode of my parameter estimate, I'm going to get 0.045. So we can see we can double or half our probability of failure by choosing one point estimate or another point estimate. So in this case, it shows how these are not good choice for two reasons. One, we can have drastic variation in the estimation of probability of failure by choosing one point estimate or the other. And the second one, this is what we're going to see next. We're going to underestimate our probability of failure by using such an estimation. Why? Because we're going to neglect the uncertainty associated with f of theta, the uncertainty associated with our joint prior probability for, in this case, mu s and sigma s. Because by using the mode, we only use the most likely value. By using the mean, we're going to use the average value, which are both not considering the uncertainty. So we can address this limitation by looking at predictive estimate. So point estimates were PF at, predictive estimate are PF tilt. Okay, we're going to look at it. We're going to look at a little recap on the standard normal space. We're going to look at how can we build our predictive estimate using a first order approximation. And we're going to review the same example we've been seeing since the beginning of the module to see how can we improve our approximation of PF to account for the uncertainty about the parameter theta. So by definition, our predictive estimate PF tilde is going to be the marginalization of theta with respect to the joint between PF and theta. So by multiplying the conditional failure probability conditional upon theta times the joint probability for theta, we add the joint between the two. We integrate with respect to theta, we're going to marginalize it. Okay, this is taking the expectation over theta for PF of theta, where theta is itself a random variable. We can go and have our predictive reliability index by simply using the same relation we saw before. So 1 minus PF, the inverse CDF, and we're going to get our beta tilde or predictive reliability index. And this predictive estimation for either my reliability index or failure probability is the one that should be favored for decision making in uncertain contexts. The question is, how can we evaluate that PF tilde? And to see this, let's first review the standard normal space. What we've been using in FOSM, form, SORM, which is really our tool in order to reduce a multi-dimensional integral into a 1D integral that is entirely function of beta, my reliability index. So we saw early on that my probability of failure is the integral. In this case, I have 2 dimensions. So in a 2-dimensional standard normal random variable. So if I transfer my problem from the original space X to the standard normal space, this is equivalent to integrating in that 2-dimensional standard normal space with respect to u for all the values g of u lesser or equal than 0. So in that case, I can reduce that 2-dimensional integral by a single unidimensional integral. How can I do this? It's because if this is my generic domain in U1, U2, and I have an arbitrarily oriented alpha vector, which define an arbitrarily oriented limit state surface. Okay, in this case, we saw in module 7, we can write this limit state surface as g of u equal beta minus alpha u. Okay, this is negative in the blue domain. This is positive in the white domain. So this thing, I can simply, because of the rotational symmetry of my standard normal space, this representation and this rotated referential contain exactly the same probability content on the blue side of the domain. So the probability density or the probability of being in that blue region or that blue region are by definition equal, because the only difference between the two is a rotation. And the standard normal space is invariant in rotation. So the probability content on this side of the plane is simply dependent on the distance between the origin and that plane. And since it's the same distance in both cases, this blue region and this blue region contain exactly the same probability. And the power of that standard normal space is not only we can make rotation, but we can reduce the dimensionality. So basically, the probability content in that blue region, in that 2-dimensional space, is equal in the probability content in that 1-dimensional region, where again we have a standard normal space, but not in 2 dimensions, in a single dimension, where the distance between the origin and that frontier is minus beta. And that reduction applied not only in from 2 to 1 dimension, but from an arbitrarily large number of dimension to 1 dimension. So once we know the distance between the origin and the failure domain, we can reduce to the integral in a single dimension. Where here we can simplify g of u equal beta plus u. Okay, that single univariate standard normal space. And this is what allows us to go from beta to PF. This is what we've seen over and over since the beginning of the course. So we're going to reuse this formulation saying that g of u, so my limit state function, is equal to beta, which is function of theta. So I am going to put explicitly the dependency upon the parameter value plus u, my standard normal random variable. So mean 0, variance 1. Now, if I want to compute the expected value for my output, I'm going to have 0, so the mean of u, plus the mean of beta. I want to have the variance of my limit state function. So it's going to be this, the variance of u is going to be 1, plus the variance of beta. Okay, so sigma square of beta. So if I want to use my first order approximation to evaluate that mean and variance, so the first order approximation for the mean is going to be the mean evaluated at its expected value for the parameter theta. For the variance, it's going to be the gradient of beta with respect to theta times the covariance of theta times gradient transpose. So then my predictive reliability index is going to be the ratio between these two quantities. Whereas we have on the numerator the mean of g of u, denominator we're going to have the standard deviation of g, so the square root of what we have here. So we're going to have mu of beta, so beta evaluated at the expected value, divided by the square root of 1 plus the standard deviation we have there. So if we put that into practice into the same example we saw earlier with exactly the same setup, we have those prior hyperparameter from US and sigma s. We have the same setup as before. Now we can regroup those into a mean vector for theta, so 15 and 5. We have here the covariance matrix. We assume that both are independent, so that on the first term here I have 5 square. The second one I'm going to have 2 square. So now I can compute using what we saw in module 7, the gradient of beta with respect to my parameter theta. I'm going to get minus 0.1.008. The mean of my beta is going to be the beta evaluated at the expected value, 1.39, the corresponding probability of failure, 0.08. The standard deviation or the variance for beta is going to be the gradient of beta with respect to theta, the vector I have here, times the covariance I defined in the previous slide, times gradient transpose 0.54. If I divide 0.08, 1.39 divide by 0.54, by the square root of 1 plus 0.54 square, I'm going to get 1.22. And what we see is that if we just take the point estimate, basically the beta evaluated at the mean value, I got 1.39. I got something slightly smaller because here I include not only the expected value, I include the uncertainty associated with my parameter value theta. My predictive failure probability is 0.11. So you see the point estimate is 0.08. I got a slightly higher probability of failure for my predictive estimate. And if we look at are we on solid ground? If we would repeat the exercise using a Monte Carlo analysis, the ground truth would be something around 0.11. So you see that the predictive solution we have here is very close to the Monte Carlo ground truth if we compare it to the point estimate we would get by only evaluating the conditional probability of failure at the expected value for the parameter theta. So the same thing for the beta. If we represent the uncertainty about my beta value by mapping here it on a Gaussian random variable where we define explicitly the mean for beta and the variance for beta using calculation we saw earlier, that would represent this dispersion in our knowledge of what the values of beta could be. If we use the point estimate beta at, by evaluating only the mean we get there, the beta till the predictive one is slightly lower. So it means that at every time we're going to consider the uncertainty about theta, that's going to have the effect of reducing our reliability index, meaning increasing my probability of failure. So whenever you add uncertainty in your analysis, that's going to lead to a reduction in beta and augmentation of that failure probability. And you can see we evaluated here that probability of failure was around 0.11 for predictive estimate. Compared to other two point predictive, we go to 0.08 and 0.45. These are not conservative, okay? Because these neglect uncertainty. They're not safe estimates to be used. Then the last thing we're going to see is how can we build a confidence region for our probability of failure. So defining lower and upper bound that are associated with a level of confidence 1 minus alpha. So we're looking for the interval either for beta or reliability index or for PF that will contain a level of confidence of 1 minus alpha. So let's say that 1 minus alpha equals say 0.95. So I want a 95% probability of include an interval that will include with a 95% probability the correct probability of failure or the correct reliability index. So to do this, I can find my lower bound for the reliability index as the mean from my beta, and the standard normal CDF inverse of alpha divided by 2 times the standard deviation. I can do the same thing by simply doing now 1 minus alpha divided by 2. So basically, I'm taking the inverse CDF to find the lower and upper bound, and then I scale it by the standard deviation of my beta. So let's look at visually with the same example we had previously. How will this turn out? So we already computed previously what would be the mean of beta, what would be the standard deviation. And if we fix a level of certainty beta that we want to reach, so in this case, I don't have the number, but it's most likely 0.9 or 0.95. If I choose 0.95, I'm going to take 2.5% top values. I'm going to take the 2.5% bottom values and looking at what is the lower and upper bound on my betas. In this case, my beta could be somewhere between 0.5 and 2.25 to include a 1 minus alpha level of confidence. So when the parameters involved in our reliability analysis, okay, so all the theta involved either in a joint probability density for f of x or theta g involve a limited function are themselves uncertain, we need to describe those using probability density themselves. And we want to include the effect of not knowing exactly those parameter value on PF by using either a predictive estimate by marginalizing out the effect of the uncertain parameters. And if we want to use the linear approximation to do so, we can follow this with that formulation that is fairly inexpensive to do. Or we can define those confidence region with a lower and upper bound. This is what is used in the standards for designing, for instance, nuclear power plant, where the specify prescribe confidence region to satisfy in order to assess the reliability of those critical infrastructure. And one thing you need to remember is that whenever you're going to use a point estimate in a case where you have uncertainty about your parameter theta, you're going to neglect this uncertainty about the parameters and you're going to underestimate the failure probability. You're going to overestimate the reliability index. So now the question that remains to be assessed, okay, but how do I know what is the prior probability density for my parameter theta? So we're going to see that in the following module 11. How can we quantify the uncertainty about our parameter theta involved in, say, f of x by using empirical evidence? How can I use observation? How can I use field tests in order to quantify the uncertainty about my parameters theta? So this is what we're going to do in the module 11, where we're going to see how can empirical data guide our definition of the joint probability for the quantity involved in all the random variable x.